friends, and welcome to another series on our mathematics education program for class 12. Even though I cannot see or hear you, I will do my best to convey to you the beauty, rigor and mystery of the subject. Contrary to popular conception, maths is a subject which can be understood and enjoyed. You start with some basic axioms or definitions, make logical deductions and come up with a host of exciting results which can be used to solve all kinds of problems. All you need is basic common sense, a little imagination and the desire to explore or discover. So, do join me on this voyage of discovery. In our series, we shall discuss the concept of a vector. You might have observed that although a large number of physical quantities such as height, weight and temperature can be measured with the help of a single real number, there are situations in which a single number is not enough. For instance, if you are travelling in a car, then you would like to know not only at what speed the car is moving, but also in which direction it is moving. Otherwise, you might end up at the wrong place. And so, we combine speed and direction in a concept that we call velocity. Other examples can be found in the field of sports. For instance, if you are playing tennis, then you need to know not only how hard to hit the ball, but at what angle to hit it, otherwise you might end up hitting sixers. Or if you have done some judo, you will know that the most essential part is the breaking of the balance of the opponent. You need to pull your opponent with a moderate amount of strength in the right direction. And therefore, the force that you use must have both magnitude and direction. Other such examples prompted us to define what we call a vector, which is a mathematical entity which has both magnitude and direction. Force and velocity are two examples of vectors. Now, how would we represent a vector geometrically? As far as the direction is concerned, it could be represented by a straight line in space with an arrow attached to it to indicate the direction. And as far as the magnitude is concerned, which is after all a non-negative real number, we could take any length to represent it. And these two can be combined with the help of a portion of that line with an arrow attached to it. In other words, a directed line segment. If the line segment begins at A and ends at B, then we call A the initial point of the vector. And B the terminating point of the vector. The vector itself is written as AB with an arrow on top of it. The vector minus AB is defined to be the vector BA. That is, you take the same line segment and reverse the arrow. Now, I'd like to ask you a question. Suppose you have two vectors AB and CD, and if they have the same length and are parallel to each other in the same sense, which means that the arrows point in the same direction, then do they not represent the same direction and do they not have the same magnitude? In other words, should they not represent the same vector? That is exactly how it is. We define two vectors AB and CD to be equal to each other if and only if they are parallel and equal in length. And so, any vector can be represented by infinitely many line segments, directed line segments rather, all of which are parallel to each other in the same sense and all of which are of the same length. A vector is often represented by a small letter of the alphabet, and we define the 0 vector to be the vector which has 0 magnitude, and it is taken to be parallel to all vectors. Geometrically, the 0 vector is represented by a single point. A unit vector is a vector which is of magnitude 1, and it could have any direction. So you have infinitely many unit vectors, and the notation that we use for a unit vector is to replace the arrow by a cap. The magnitude of a vector A is denoted by the symbol modulus of A, or simply A. Note that the magnitude of a vector is a non-negative real number. Now, we have another name for real numbers, that is scalars, to distinguish them from vectors. What we would like to find out now is there any way of combining vectors with each other or scalars with vectors? First, we explore the possibility of multiplying a scalar lambda with a vector A. Recollect that the vector has two parts to it, a magnitude and a direction. The magnitude itself is a non-negative scalar. So, an easy way of defining the multiple of the vector A by the scalar lambda would be to multiply lambda by the magnitude of A and leave the direction unchanged. This would work as far as a non-negative scalar lambda is concerned. What happens if the scalar lambda is a negative number? In that case, we could define the new vector lambda A to be one which has magnitude mod lambda into the magnitude of A and is in the opposite direction to that of A. Let us see how we would represent this vector lambda A geometrically. If this is my vector A, then the vector lambda A would be naturally parallel to A, and its length could be smaller or greater than A depending on whether lambda is of length less than 1 or greater than 1. This would be true if lambda is positive. If lambda is negative, then the vector would be in the opposite direction to that of A. In other words, we call it anti-parallel to A to distinguish it from parallel in the same sense. Okay. So, this is the meaning of lambda times A. I have a little exercise for you now. Suppose you have two scalars lambda and mu. Can you prove, rather I leave out the middle bracket, so this can be written as lambda mu A. Can you prove that lambda mu A is equal to mu of lambda A, and both are equal to lambda mu, the scalar, multiplied by A? So, this is the result that you can try to prove. Lambda of mu A is mu of lambda A is equal to lambda mu of A. Try it. It's very easy. All you need to do is take combinations of the signs of lambda and mu. If they are of the same sign, then we find that the vector, any one of these vectors, will be parallel to A in the same sense. If they are of opposite signs, we find that any of these vectors will be anti-parallel to A, and of course, in all three cases, the magnitude turns out to be mod lambda, mod mu, mod of A. So, wasn't that an easy exercise? And now we come to the second question. Is there any way of combining two vectors? What is the need to combine two vectors? I'd like you to imagine a game of football. Suppose a ball is moving with velocity A and a player kicks it in such a way as to give a stationary ball a velocity B. which direction and with what speed will the ball begin to move? In other words, what would be the resultant velocity of the ball? Is there any way of adding these two vectors A and B to find out the resultant? Yes, there is, and that is called vector addition. There are two ways of defining vector addition. One is called the triangle law of addition, and the second the parallelogram law of addition. Let us first look at the triangle law of addition. Suppose we have two vectors, A equal to AB and B equal to CD. How would we add these two vectors? Well, the first thing that you do is to draw through B a line equal and parallel to CD. Let us call that BE. So, by the definition of equality of vectors, the vector BE is equal to the vector CD. In other words, the vector BE is the same as the vector B. Then we define the sum A plus B of the vectors A and B as the vector AE. Note that what we have done is to move the vector CD, that is the vector B, parallel to itself so that its initial point coincides with the terminating point of A. In other words, you are travelling now from A to B and from B to E, and that is equivalent, as we all know, to travelling from A to E. That is exactly how the triangle law of addition is defined. And now let us go on to the parallelogram law of addition. Do you know the spelling of parallelogram? In that case, I will just use a short form, PAR with an M on top of it. The parallelogram law of addition. Let us start once again with the vector A equal to AB and B equal to CD. Now, here we are going to draw through A line parallel and equal to CD, and let us call that line AE. Sorry, we already have E, so let us call it AF. Once again, by the definition of equality of vectors, we find that the vector AF is equal to the vector CD. In other words, the vector AF is also equal to the vector B. Here's our A, here's our B. In this case, we have drawn a vector parallel and equal to CD through A. In other words, what we have done is to move the vector B parallel to itself so that its initial point coincides with the initial points of A. And the definition of A plus B according to this law is given in the following way. You complete the parallelogram with the two sides as AF and AB. And let us call that parallelogram ABEF. The diagonal of that parallelogram is defined to be the vector A plus B. Note that since the vector BE is parallel and equal to the vector AF, being opposite sides of a parallelogram, therefore, BE also represents the vector B. And so, whether you use the triangle law or use the parallelogram law, you get one and the same meaning of A plus B, that is AE. Hence, it is easy to see that the triangle law and the parallelogram law are equivalent. Now, I would like to discuss some properties of this vector addition. Before we move on to those properties, is there some way of defining A minus B? Well, that is easy to see. Since we already know the meaning of minus of a vector, A minus B can be defined as the vector A plus the vector minus B. Some more properties of addition. You remember the vector 0. It is clear, I hope, that A plus the vector 0 will be equal to the vector A. Okay. 0 is merely a point geometrically, and it will not alter the vector A if we add it to the vector A. Some more non-trivial properties. Is this property true? A plus B is equal to B plus A. In other words, is vector addition commutative? That is the word used for this property. Let us examine. Consider the vector A represented by the directed line segment A, B. And consider the vector B represented by the directed line segment, as before, BE. Then we all know by now that the vector A plus B is defined as the vector AE. Now, let us reverse the roles of A and B. We begin with the vector B and draw from its terminating point the vector A. This is supposed to be the vector A. Well, now these two lines are parallel to each other. We complete this parallelogram, or rather we join B and E. Forget about the previous triangle. Look at this triangle. BE is the vector B, EF is the vector A. By the triangle law of addition, the vector B plus A is the vector BF. Right? Now, let us look at this triangle again. We find here that this is nothing but a parallelogram, right? And that is why we find that this line is equal and parallel to this line, which means that this vector, which we had earlier said is B plus A, is equal to the vector A plus B. In other words, the commutative property for vector addition is true. There is another question that we would like to ask. There is no dearth of questions. We can go on asking questions. This question says that if you have three vectors A, B and C, you first add B and C to get a vector and then add A to that vector. So, you have A plus bracket B plus C. We would like to know that if we first added A and B and then added C to it, would the answer change? In other words, is the associative law true for vector addition? Let us examine this proposition. Let me start with three vectors A, B and C, represented by the directed line segments A, B, B, C and C, D. Respectively. The vector A plus B is given by AC according to the triangle law. And again using the triangle law, the vector A plus B plus C is given by the vector AD. Right? Now let us try to calculate A plus B plus C. First let us calculate B plus C. B plus C by the triangle law is equal to the vector BD. And let us apply the triangle law once again to get A plus B plus C is equal to AD. In other words, the vector AD represents both A plus B plus C as well as A plus B plus C. And so we have proved that the associative law is true for vector addition. The associative law helps us to define A1 plus A2 plus A3 plus AN for n vectors A1 to AN. This is done inductively using the associative law. The positioning of the brackets is not material. Geometrically, we can look at it like this: A1 plus A2 plus A3 plus A4 and so on plus AN is equivalent to the vector drawn from the initial point of A1 to the terminating point of AN. And this can easily be seen by applying the triangle law two at a time and then seeing that the brackets are not material at all because of the associative law. So, in effect what we have is that in travelling from this point to this and this point to this and so on up till this point, you have in effect travelled from the first point to the last point, and that is the sum of all these vectors. Now, the next question that we would like to ask is, what is the relationship between scalar multiplication and vector addition? In other words, do we have some kind of property like this? If we have two scalars, lambda plus mu, is lambda plus mu of A equal to lambda A plus mu A? And a second question could be that if we have two vectors A and B and a scalar lambda, is lambda A plus B equal to lambda A plus lambda B? These properties, if they are true, would be called distributive properties. Let us look at the first of these, which is extremely easy to prove, although slightly cumbersome because you have to take a number of cases for the sign of lambda and mu. Geometrically, if this is the vector A, then the vector lambda A would be something like this, and the vector mu A drawn from the terminating point of lambda A would also be in the same direction. And so, lambda plus mu of A would be the vector starting at the initial point of lambda A and ending at the terminating point of mu A. If we call this A and this B and this C, then the vector lambda A plus mu A would be the vector AC. It can easily be seen that this vector AC has magnitude equal to this length of AB plus the length of BC, that is lambda times mod A plus mu times mod A, which we know by the same property in ordinary real numbers is equal to lambda plus mu of mod of A. And we can see that this is nothing but the magnitude of the vector lambda plus mu A. In other words, the magnitude of the vector AC is the same as the magnitude of the vector lambda plus mu of A, and the direction, all of you can see, is of course the same. And so, in the case lambda and mu are both positive, we have seen quite easily that this property is true. The other cases, although slightly cumbersome, are not difficult to prove at all. All that we have to do is to draw mu A in the opposite direction in the case mu is negative, and then see what happens to lambda A plus mu A. I think it would be an interesting exercise for you to complete. Let us now look at the second property, which we will try to show is also true, and that is lambda A plus B is lambda A plus lambda B. Let us draw the vectors A and B represented by OA and OB respectively. And now let us draw the vectors lambda A and lambda B. Note that lambda A has to be parallel to to the vector A. Let OC represent lambda A and OD represent lambda B. And now let us construct, using the parallelogram law, the vectors A plus B and the vectors lambda A plus lambda B. By the parallelogram law, the vector A plus B will be given by the diagonal of the parallelogram with sides OA and OB, which we can call OE. So, A plus B is equal to OE. And similarly, we complete the larger parallelogram with sides OC and OD, and the diagonal of that parallelogram, that is OF, let us call it, will be the vector lambda A plus lambda B. It is very easy to see naturally that this diagonal OE will be part of the diagonal OF. Okay. Now, we have to show that the vector OF, that is lambda A plus lambda B, is equal to lambda times A plus B. In other words, it should be lambda times the vector OE. Now, let us just look at this diagram. We have here similar triangles OBE and ODF. The triangle OBE is similar to the triangle ODF. And that means that the corresponding sides will have to be proportional. In other words, OB by OD will have to be equal to OE by OF, or the other way around, OF by OE must be equal to OD by OB. Let us write that on the next page. OF by OE is equal to OD by OB. Can you see that? Just look back at the diagram. Right. And because of this, we find that since OD is lambda times B and OB is B, if you divide the magnitude of OD by OB, you will get exactly lambda. And therefore, OF is equal to lambda times OE. And this means that the vector OF will be lambda times the vector OE. Since the two vectors are clearly seen to be parallel and they have the same magnitude, therefore, the two vectors must be equal. And we have therefore proved, let us go back to what was OF, we have proved that OF is lambda times OE. In other words, lambda A plus lambda B, that was OF, is equal to lambda times A plus B, A plus B being the vector OE.